Good afternoon. Here I yet again for another lovely session of CENG 3325 Structural Analysis. This will be the 28th lecture in the video series, and in this lecture I'm going to be working through a long-form example of applying the force method to trusses. So here's the problem I'm going to work through, and this is going to be just a single long-form example. Force method for trusses. So consider this here. So we're going to have a 5-member 4-joint truss, and we're going to have pin supports here and here. Like this here. And we have dimensions of 16 feet and 16 feet and 12 feet. 16 feet, 16 feet, and 12 feet. And 12 feet in the vertical. Then we have a load applied to this, 10 kips in a direction 30 degrees below the horizontal. 10 kips at an angle of 30 degrees below the horizontal. Like so, 30 degrees below the horizontal. And we are also told its material properties and cross-sectional properties. We are told that all members have a cross-sectional area equal to 2 inches squared and a modulus of elasticity equal to 29,000 KSI. A modulus of elasticity equal to 29,000 KSI. So these are steel members. And I wish to find the horizontal deflection at joint D. I want to find the horizontal deflection at joint D. And in terms of joint names, well, I'm going to give this A, B, C, and D. So we're looking for the horizontal deflection at this joint here, under these loads. So looking at this, if this were, we have already looked at things like this previously in the semester. We saw this kind of thing previously when we looked at the method of virtual work when applying it to trusses. So at first it seems relatively straightforward. However, take a look at our reactions here. Look at the number of reactions. We have not 3 reactions but 4. So the first thing I'm going to do is investigate the determinacy. First thing I want to do is investigate the truss determinacy. That's going to be my first step. Investigate truss determinacy. So here, I'm going to use my old equation from statics, which is m plus r is equal to 2j. When m plus r is equal to 2j, I have a statically determinate truss. And so m, my number of members, is going to be 5. My reactions, I have an AX, an AY, and a BX and a BY, so R is equal to 4. Then I have 4 joints, so 2 times 4, so 9, well this is clearly not equal to 8, so this will then be indeterminate to the first degree. To the first degree. So in turn, I need to choose one redundant force. And because I've worked with many trusses that are simply supported with just a pin on the left and a roller on the right, I think I'm just going to go ahead and pick I think I'm going to pick BX as my redundant. Although, of course, we really could choose any of them as my redundant reaction. So I'm going to pick BX as my redundant reaction, and this is going to be the force method. So basically our overall approach here, as we looked in the theory video last time, my overall approach will be as such. I want to turn my indeterminate system into a determinate one. System into a determinate one. And I do this as follows. Remember, I'm going to use something like this. I'm going to have a delta B naught plus delta BB times, that would be BX here. This is what I'm going to try to implement. This is going to be my deformation of the truss at B under real loads but with redundant removed. Redundant removed. My BB, my lowercase delta BB, this is the deformation at B due to a unit load at B. And Bx will be my actual reaction at B that will bring this back to equilibrium. This is my reaction at B. And I could go and put subscripts of x on these. I think I'm just going to leave them off for brevity's sake because all of my deformations here that I'm calculating are in the x direction. It really becomes important to include the subscripts if you are doing a system with multiple deformations in different directions especially. All right, so now in step 2, we are going to look at analyzing this. So step 2. And step 2 is all going to be about finding this delta B naught. However, when finding that delta B naught, I'm going to use a full method of virtual work or a full virtual work calculation within just that step. So step 2 is going to be to find delta B naught, again, the deformation of joint B with Bx removed and real loads present. And real loads present. Okay, so let's go ahead and get that. And 2A, the first step of 2A, is going to be essentially to find the internal member forces of under these real loads. I'm going to apply the virtual work method that we looked at a couple weeks back. Find the internal member forces to use as part of virtual work. So let's go ahead and do that. I'm going to draw out this truss. Now, for brevity's sake, this video is going to be long enough as is, so I think when I'm going to work through this, or when I did actually work through this myself on pen and paper, I went and did all of the calculations manually using, actually used the method of joints from statics. Now, you could do that, and actually that's how you would solve it, or you could use the method of sections, whatever method you choose. But for the sake of brevity, I think I'm just going to give you the results of that analysis rather than writing through every single one of those calculations, because this video is going to be long enough. So I'm going to go ahead and I went ahead and broke down my force at D into x and y components. So in the x, I have 10 cosine 30 toward the positive x direction, and then 10 sine 30 to the negative y direction. And then the reactions, I'm going to have an AX, an AY, and a BY. And a BY here. And when I went ahead and got the reactions by static equilibrium on the rigid body, basically the entire truss as a rigid body, equilibrium on truss rigid body, I got the reactions. I got that, let's see, AX is equal to just the opposite of this, so that is negative 8.6603 kips. I then found AY. I took a moment about B and balanced that, and found that AY is equal to negative 11.4952 kips. And then I also found that BY, by taking a moment about A, is equal to 16.4952 kips. and then I check them with sum of forces in the horizontal and vertical directions. So now I wanted to get the forces in members AB, AC, BC, CD, and BD. And I did that via method of joints. I just worked through one joint at a time and found via method of joints. Also, you would want the dimensions on here for this. To get that, you would probably want the dimensions. So I think I'm going to keep writing those as I go. As a reminder, this is 16 feet here, 16 feet here, 12 feet in the vertical, 12 feet in the vertical here, and 16 feet. Each of these bays is 16 feet wide. Each of these bays is 16 feet wide. And our slopes here, these are 3, 4, 5 triangles. So via the method of joints, again, I started at one joint, and then you can either start here or you can start here, and you just move your way through the truss. Again, just very basic elementary statics. Method of joints, I found the following member forces. Oh, I probably should list that here. Method of joints. I found following member forces. Following member forces. And let me list this by member. I have a nice table here that I'll just write out. And so member and then the force I found. And this is in kips. These are all going to be in kips. Okay, we have AB, and let's put a line there, and then AC, BC, BD, and CD. BD and CD. So AB has a force of negative 6.667. So 6.66 repeating. AC, I found 19.159 kips. BC, I found a negative 11.495 kips. And BD, negative 8.333 kips, 3 repeating. And CD, I found 15.327 kips. Again, in step 2A, I'm finding the internal member forces due to the real loads without B present. Now, my next step in my virtual work method for step 2 is going to be to apply a unit load to joint B, because that's where I'm interested in the deformation at. So step 2B will be to apply a 1 kip load, and I'm doing a 1 kip load because I'm using KSI, and that's compatible with the units I'm using. A 1 kip horizontal load at B. A 1 kip horizontal load at B. As we need to find the deformation at joint B without the redundant. Deformation at B without the redundant. Without redundant. So I'm going to redraw my truss and show the loads here. And if you recall the virtual work method, in this step, the real loads on the truss disappear. So I'd still have a pin here and a roller here, and dimensions horizontally of 16 feet, and also 16 feet in this horizontal dimension here. Here to here is 16 feet. And in the vertical, it's 12 feet. And we have, again, our 3, 4, 5 triangle. 3, 4, 5 slope triangle. Now the loads on this, we're going to have only a single 1 kip load here. And we have our same joint names, A, B, C, and D. And this actually comes to a very simple structural analysis. When you run through the equations here, you will find that the forces in every single member except AB is 0. So our virtual forces here are quite simple. The reactions, AX is going to be equal to negative 1 kip, and both AY and BY are both equal to 0. AY equals BY equals 0 kips. And so member virtual forces or in other words, what's going to happen here is that the load comes in, this unit load comes directly in, comes in horizontally on joint B, and just is delivered straight through, that looks like a really bad A, comes straight through member AB and is delivered directly as a reaction at joint A. So our virtual member forces are as follows. Or maybe I can write a table member. And you can do this using the method of joints or method of sections, whatever you need to see, whatever your preferred method is. And so here, member and then virtual member force, internal force, and this is our FV. And this will also be in kips. And so we have the same AB. I'll keep this member order the same in all my tables. AC, BC, BD, and CD. And it's just going to be 1, 0, 0, 0, and 0. Okay. Then next, I guess I would call this 2C, step 2C. I will apply virtual work to calculate delta B naught. To calculate delta B naught, capital delta B naught, that is the deformation at joint B due to the real loads if the redundant reaction at B is removed. And so our generic equation for the virtual work method is 1 times delta is equal to the summation of FV times FL over AE. FL over AE. Now for our particular one, if we look at these two tables, the only thing, when I multiply these FVs in here, the only member that doesn't come to 0 for the summation is our member AE. So basically we just have to do 1 kip times delta A naught, and it won't always be this simple. It's usually not this simple, but for this example, things did collapse nicely. So it's just the summation for member AE, member AB here. And so this then comes to just plugging and chugging. 1 kip times delta A naught is equal to, now the real load on this, or the virtual load in that member is 1 kip. And the real load, if you look at the previous table, is negative 6.666 kips, or 6.7. Its length is 192 inches. And then like all of the members, its area is 2 inches squared. And it has a moment, not a moment of inertia, a modulus elasticity, this is steel, of 29,000 kips per square inch. And so then multiplying that out, you can find that delta A naught is equal to negative 0.02207 inches. So with the redundant removed, with the redundant removed and real loads present, joint B moves 0.02207 inches to the left. So without that redundant force, basically what happens is this thing moves down and to the right. There's this large 10 kip force pulling the whole truss down and to the right. These stretch out and the bottom cord, so the top cord goes into tension. Basically this is negative bending. The top cord goes into tension, the bottom cord goes into compression, and so joint B actually ends up moving to the right, or sorry, to the left. And our next step is going to be to apply virtual work a second time to find our lowercase delta BB. All right, so let us now continue with part 3, or step 3. So we have our capital delta A naught. Well, actually, that should be capital delta B naught, should it, I suppose. That should be capital delta B naught there. So that should be B naught, and that should be B naught, and that should be B naught here. But that is still correct. That is the distance the joint B will move when the real loads are applied to the truss, but the redundant is not. So for step 3 then, I want to use virtual work. I want to use virtual work to find delta BB. And this is the unit deformation, or the deformation at B. Again, delta BB, lowercase delta BB, is the deformation or displacement at B due to a unit load applied at B. Applied at B. So I'm just going to set my truss up again. And it can be like this. Let's go ahead and set this up. Draw this out. And we're just going to have a 1 kip load on joint B to the right. So I have a 1 kip load here. Let's see. And then I can go ahead and put the dimensions on there again. 16 feet and 16 feet. And 12 feet in the vertical. And then we have our 3, 4, 5 triangle for the slopes of these diagonals. This would be a 3, a 4, and a 5. So now consider this for a moment. We are kind of using virtual work here in a way that it's really not necessarily intended to be used. And because if I look at the equation for virtual work for trusses, I have this 1 kip times delta, or 1 times delta equals FV times FL over AE. Times FL over AE. However here, this is going to be, the load distribution in this is going to be the same as the load distribution in this problem here, because it really is the same problem. So if for this case, the only member that has any force, and joints A, B, C, and D, the only member that has any force is member AB. Any force is member AB. So this delta, first of all, this delta, this capital delta here from our truss formula, or our virtual worker truss formula, this is our BB. And our FV is just going to be 1 kip, because that's the unit load that that is the load that will be present in member AB. So member AB has a force of 1 kip in it. And we saw that previously. A force of 1 kip in it. 1 kip tension. So I don't actually need to do the summation here. I don't need that summation term that we normally have. And I probably should have drawn that summation there. We don't need to have that summation. And if I write this thing out more appropriately, it might be 1 kip times delta BB is equal to 1 kip times FL over AE. But the 1 kip cancels out, so delta BB is just equal to FL over AE, where F would be the load produced by the actual loads on the structure. However, for this step of the process, the actual load is just a 1 kip load as well. And so that's just 1 kip times the length of 192 inches divided by the area of 2 inches squared, and then times 29,000 KSI. So the second step, or this third step, I suppose, is quite simple. Even though we are technically working through a full virtual work method here, because we've already worked with this problem a lot before, or we've already worked with the case of having the 1 kip load to the right on joint B, we can find the, we can see that the virtual system, again, for this particular case, for step 3, the virtual system and the real system are the same thing, again, virtual and real, in the context of the virtual work method. And that comes then to 0.0031 inches. 0.0031 inches. Step 4. So now I know, well, what do I know now? This is my delta BB, my lowercase delta BB. Again, this is the deformation at B due to unit load applied at B. So step 4 then, just like we've done in force method for beams, I'm going to balance the deformations. And this is just simple algebra here. So capital delta B naught plus lowercase delta bb times bx is equal to 0. And just putting in our known values, negative 0.02207 plus delta bb times 0. Actually, I'll go ahead and I want to put that number in there, times 0.00331 inches and inches times bx is equal to 0. And bx, that's easy to solve for, and you'll find that bx is equal to 6.667 kips. So I now have solved my redundant force. The reaction at B in the horizontal direction is a 6.667 kip force to the right. So we have now turned this truss into a statically determinate truss. We have removed the redundant and back solved for it, and now that we know the value of that redundant force, we can just analyze this like we would any statically determinate problem. So let's see here. Step 5, analyze the now determinate truss. Now determinate truss. And so let's consider what this would look like. The truss will now be a simply supported truss with an extra load applied to it. And so I have a pin and a roller. Let me give some names here. Let me give us some names, A, B, C, and D. And in terms of forces, I'm going to have my AX, my AY, and then I'll have my BY, and then my redundant force again is going to be applied as a load. So this is going to be 6.667 kips, or 6 2/3 kips. Then I have the real loads, these appear again, 10 sine 30 and 10 cosine 30 and 10 cosine of 30 degrees. Then for completion's sake, I could go ahead and put the dimensions on here. I'll have my 3, 4, 5 triangle. Let's see, 3 in the vertical, 4 in the horizontal, and heights of 12 foot and height of 12 foot and widths of 16 feet. (16 feet here and 16 feet here). So so now I'm going to analyze this, and when I say analyze it, what am I looking for in particular? Well, if I were to go back to the very beginning of the problem, I was asked to find the horizontal deflection at joint D. So we actually have one more virtual work process to apply, and I'm going to apply virtual work to find the displacement at D. And this is a pure virtual work. We're not going to be interfacing this with the force method again. This is just virtual work like we've seen throughout the semester. So apply virtual work to find horizontal displacement at D. Displacement at D. Okay, so first of all, let's get the forces, and this one really isn't too bad. If you do a balance of forces in the x direction, that will lead you to that AX is equal to, this one's very easy to solve, negative 15.327 kips. If you do a sum of moments about point A, counterclockwise positive, that will tell you that AY, or BY, suppose, is equal to 16.495 kips upward. upward. And then if you do a sum of moments about point B, that will allow you to get AY. And that then comes to, that's jumped ahead there. A sum of moments about B will tell you that AY is equal to, let's see, negative 11.495. 0.495 kips. So we have our reactions. Again, for the sake of time, I am not necessarily running through all the calculations, especially when those calculations are just basic statics. So then, using statics then, either method of joints or sections, find the internal member forces. Find the forces in all members in the truss. Forces in all truss members due to real loads. In all truss members due to the real loads. And in this context, the real loads are all of the loads applied to the structure. All truss members due to the external loads. Real external loads. Okay, so we have that, and let me just go ahead and provide these. Again, I hope by now you know how to do this. When I did this, I just worked through the method of joints from one side of the truss to the other, and really it isn't so bad. Or it isn't too bad. So I'll just create another table again. Member and real member force. In kips here. And we'll have AB, let's see, AB, AC, BC, BD, and CD. And CD, like here. And the forces you'll get for here, you'll actually get 0 on member AB. You will get, let's see, excuse me, you'll get 19.159 on member AC. BC will have negative 11.495. And BD you'll have negative 8.333. And CD, you'll have 15.327. 15.327 kips. So we have that. And maybe I could even put some labels on these here. This would be maybe 5A. 5A, get real internal forces, or real forces. And then 5B is going to be to get the virtual member forces, or virtual internal forces. Get the virtual internal forces. And this is going to be the forces in each member due to a unit load applied at joint D. A unit load applied at joint D. We're interested in the horizontal deflection at joint D, so we are going to put a unit load in the horizontal direction at joint D. So if we have a truss here, let's draw this out again once more. Like this. With our pin and our roller. And A, B, C, and D. And we apply a 1 kip load at D, and I'm just going to go ahead and apply it to the right. Oh, my D seems to have disappeared and become a C. But we will apply a 1 kip load to the right. 1 kip, and all my dimensions are still the same, but I hate leaving having a drawing without dimensions on it, so let's go ahead and finish that out. Just really bothers me for some reason. So 16 feet, and 16 feet, and 12 feet. And our 3, 4, 5 angle. 3, 4, 5 here. And so I think I'll just go ahead and give you these the values for these forces. Again, I hope by now you can do this. This is just literally basic statics. And so find virtual internal forces. And when I did that, I found the following. So member, and then FV, F sub V, the virtual force in that member. Let's see, let me go to my table. AB, AC, BC, BD, and CD here. And then the virtual member force, or the internal force from the virtual load, AB is going to be 0, 1.25, negative 0.75, 0, and 1.0. And so those are my virtual internal forces. And then 5C, the last step, will be to apply virtual work. Apply the combined virtual work equation. And so, since all members have the same AE, well, maybe I can show it like this. Initially, we have the formula 1 times delta is equal to the summation of FV times FL over AE. However, because they all have the same area and cross-section, I can pull these out of the sum. Same area and modulus of elasticity, same E and A for all members. So what that allows me to do is just say, okay, well, instead, 1 times delta is going to be equal to, and I guess I could put a delta D here because we are talking about delta D, the change in position at joint D in the x direction. And I can just pull that out and say, okay, that's 1 over AE times the summation of FV FL. So I'm going to create a little table, and this will be the last table of the problem, I promise. So member, and it's going to be quite a large table though. And then F, and this is going to be the real member forces in kips, or the forces from the real loads. Then I'll have FV also in kips, and this is the internal forces from the virtual load. Then I'll have L, the length, and this will be in inches, and I'll just multiply all this together in the last column. F times FV times L. And notice I am using consistent units across this thing. So I have AB, AC, BC, BD, and CD. And the forces will be 0, 19.159, or 159, yep, 19.159. All this stuff was just derived previously. I'm just combining it together, or was calculated previously. Negative 11.495, negative 8.333, and then 15.327. FV will be 0, 1.25, negative 0.75, 0, and 1.0. And then the lengths, these are just the feet converted to inches. 192 inches, 240 inches for the diagonals on the hypotenuse, 240. And this is going to be 144 for our vertical member that's 12 feet high, and 192 inches for the other horizontal. And so multiplying these out, well, these two just go to 0, so that's one less thing to worry about. And then 5,747.6 for member member AC there. And for member BC, I got 1,241.48. And then for member CD, I got 2,942.77. 0.77. 0.77. And so then all I have to do is sum this up, and that will come to 9,931.84. Now I can finally apply this equation, and so let's say that delta D, and I guess I could call this delta dx to be proper, delta dx is just going to be equal to 1 over EI, or not, sorry, EA, too used to bending, 1 over 2 inches squared, and that's our area. And our moment of inertia is 29,000 KSI. Again, pardon my harsh voice tonight, or hoarse voice tonight, a little bit under the weather. 29,000 KSI times the result of my summation, which comes to 9,931.84. And when you take this and divide it by these, you will get, or at least I got, 0.171 inches. 0.171 inches. And assuming I didn't make any math errors, which is certainly possible in something like this, but assuming we got it right, or assuming we've got didn't make any kind of simple math errors, that is the final answer. So the method is definitely right. I think I've checked this thoroughly enough that it's correct, but you never know when you come up with your own problems. Sometimes you end up with things that aren't perfect and exactly right. But the method is correct, unless there's a math error, which I don't think there is. I do think I did check this one pretty good, but you never know. So as a review, here's how we applied the horse method to trusses. Let's consider this. So we first figured out how many redundants we needed, and in this case we only needed one redundant force, and I chose to do BX because that would, the reaction BX, because that would turn this into a simply supported truss. Then I ran through and set up my my force method equation, saying I'm going to need each of these things. I'm going to need a delta BO, or a capital delta BO, and a lowercase bb, delta BB, or lowercase delta BB. And I'm going to apply the force method equation to solving for BX, my redundant force, for both the capital delta, where I'm finding the deformation under the real loads, and for the lowercase delta. For both of them, I went and found I did a whole virtual work method just to find those individual quantities. And so then, once I had those, I combined together the results from two different virtual work processes to produce my final reaction force, my redundant reaction. And then once I did that, once I had that value, the truss was then statically determinate, and we could solve for whatever final quantity we wanted, which in this case was the deflection at a completely different joint D. And to do that, to find that, I had to run through the virtual work method for trusses one last time. So just like in our cases of force method for beams, remember back in the previous videos for beams, we often ran through the same thing multiple times. We often ran through the whole series of deflection calculations or deflection integrations from load to shear to moment to rotation to deflection. We often ran through those, that whole cycle multiple times. And we have to do the same thing here with the force method for trusses. So it can be quite involved, and as far as where you use this, often you might use this to calibrate software, make sure you have something, or you're using a piece of software properly, or you can use it as a quick hand check method, relatively quick hand check method. Or you might use this as a, besides learning base principles, or you might build a piece of software around this. A lot of the commercial structural analysis finite element software uses principles like this when calculating deformations of frames. All right, well, that'll do it for now. Sorry, my voice is betraying me this late at night. Again, let's see. Again, thank you for watching. Hope you all enjoyed this. Hope you all learned a few things. I'll hope to see you again next time. Let me know if you have any questions. I will see you again. Well, actually, for my class, I'll see you tomorrow morning for class. But let me know if you have any questions. Hope you all enjoyed this. Hope you all learned something. And as always, thank you.